Okay, hi everyone, let's start. So today, tutorial 3, we're going to talk about the first kind of deeper model that we're going to see. It's called the Multilayer Perceptron. Okay, so more specifically, what we're going to talk about are fully connected layers, one of the core building blocks of deep networks. We're going to show some examples of activation functions. Then we're gonna implement a two-layer, multi-layer perceptron from scratch, just doing everything ourselves to really understand how it works. And then we'll see briefly an example of backpropagation when we implement that, and then we'll show a more advanced implementation of an n-layer MLP using built-in modules from PyTorch. Okay. So let's start. So first, let's remind ourselves what a perceptron is. So we saw it last time. I defined it as this hypothesis class. It's basically the class of functions that have some nonlinear element-wise activation phi applied to an affine transform of the input x. Okay, so this is the these functions in H are functions that represent the model, the perceptron model. Okay, so just to look at it schematically and to see kind of its inspiration. So this is a graphical representation. You can see we have just a weighted sum of all the input elements of X, and then an element-wise activation phi. Kind of looks similar to this biological neuron, which is also sometimes why these single perceptron elements in the deep networks are also called neurons. So a biological neuron has also kind of inputs that go into its dendrites, and it creates an action potential on its axon, which connects to other neurons, dendrites, and that's kind of the biological, at least, inspiration. Not that it's actually the same. Okay, so last time we basically just took this model. We said that our element-wise activation function is the sigmoid function, and we called it logistic regression, which is actually, if you remember, a classification model. So we did the binary logistic regression and multi-class logistic regression cases, and we implemented them last tutorial. Okay, so the limitation of logistic regression was it's actually linear classifier. So can you think about in what sense is it linear though? Because since we have a nonlinear function, so what's meant by the fact that it's a linear classifier? Any ideas? Okay, well, it's linear in the sense that the decision boundaries that it can create are straight lines or linear. For example, if we have only two features, x1 and x2, and these are our samples, and then this kind of model can separate them. This is a linearly separable data set. However, this kind of model can't create any nonlinear decision boundaries. For example, if we had a XOR data set, which would look like this, two features, and we had a plus sample here and a minus sample here, there's no kind of linear hyperplane that can separate. Okay, so in this sense, it's a generalized linear model, even though we have a nonlinear function. Okay, so now let's look at the MLP model. So an MLP model, as you can guess by its name, it has some number of hidden layers, and each layer is composed of these perceptrons. Now, for example, here, each yellow node is a single perceptron. So each layer has multiple perceptrons, and we have multiple layers containing multiple perceptrons in our model, generally. Okay, so the input layer is not counted, but the output layer is counted. So for example, this would be a 2-layer MLP, and this would be a 5-layer MLP. Okay. So to formalize it a bit, each layer L would operate on the output of the previous layer in the following way. So it takes this affine transform of the previous layer and applies, again, an element-wise nonlinear function. But now note that the weights here are, this is a matrix of weights, okay? So you can think about it as a matrix that each row in this matrix are the weights of one of the neurons. Okay, so in each layer you have multiple neurons, and that's why for each layer you have a matrix. Each row of the matrix are the weights for that neuron. Okay, is that clear? So each such layer is also referred to as a fully connected layer, since every neuron is connected to every single output from the previous layer. All the connections are there. Each one is, of course, weighted. Each neuron computes a weighted sum and then applies the activation function. Okay, and for the first layer, we simply say that the y of the previous layer is the input of the model. Okay. So if you have a sample xi, as you saw before, then the elf layer of the MLP kind of can be, this is not really a formal expression, but you can see kind of what it does. It computes, this time, as opposed to what we saw in, for example, logistic regression, it computes a nonlinear function of the weight combinations, as you can see here. So there's a theorem that says that actually an MLP with more than one hidden layer can approximate any function. It's a universal approximator, so that's why it's a useful and very strong hypothesis class. If you use this hypothesis class, then at least there's a theorem that states that you can approximate almost any kind of function. And though it's not always easy, it's fully differentiable. So you can use the chain rule to just calculate the gradients that you need. Okay, and as opposed to, for example, what we saw with logistic regression, you can create nonlinear decision boundaries because of the fact that you have now nonlinear dependencies of the combinations of the W's and the X's. So for example, you can see here a few examples of decision boundaries. When you increase the depth of the network and the number of parameters, in this example, you can see like kind of severe overfitting in these cases at least. You can see just a few outlier samples here caused kind of a very strange decision region here. But still, it shows you like the kind of powerful representation power this model has. Okay, so what are activation functions? Like I said, usually we use some kind of element-wise nonlinearity between the layers after each weighted sum that we do. So the question is, first of all, why do we even need them? Any ideas? What do you mean? If you wouldn't have linearities at all, then basically you would have an affine transform multiplied by another affine transform. So basically you have a bunch of matrices that you multiply one. So you can equivalently say that there's just one matrix doing the whole network. So it's just like one linear operation. The fact that you have these nonlinearities breaks everything up and gives you the representation power. So common choices are, first of all, the logistic function that we saw before. And there's also the hyperbolic tangent, which has an advantage in some cases that it's scaled to -1. So these were very common in the old kind of neural networks. They're less popular in the deep networks for reasons that you'll see. I'll just show you a small example now, and we'll see it also in the lecture. And the more popular activation function that's used in many deep networks, especially in convolutional networks, is the ReLU activation function, which is short for rectified linear unit. It's very simple. It's basically just the max of its input and 0. So for the whole negative axis, it's just 0, and then it's just a linear function. And the interesting property is that its gradient is either 1 or 0, depending on where you are on the input. So let's quickly visualize this. Okay, so here are our examples. So you can see the sigmoid function and the hyperbolic tangent, which is kind of scaled. And you can see here the gradient of these functions. So for example, you can see the sigmoid function has a maximal gradient of about 1/4. So one of the things that this causes is what's known as vanishing gradients, which means that when you have a deep network and your gradient for each layer is kind of restricted by a kind of a small number, so you're basically, when you do backpropagation, you're multiplying all these small numbers. So you might get gradients that are very, very close to zero the deeper the network you have. So this is kind of a problem with the sigmoid. That's why it's not used anymore, at least for deep networks, usually, even though there are ways to mitigate that you will see, I think, in tutorial 5, things like batch normalization and things like that can really help. But basically, the motivation to use ReLUs are, it does mitigate somewhat this vanishing gradient issue because its gradient is either 1 or 0. Now, when it's 1, you can say it does vanish, but it does have other properties that, since sometimes you can have dead neurons, which always output 0 because of the ReLU property. But some people claim, at least in some papers, they say that it promotes sparsity because the weights after such dead neurons don't matter. So we actually have kind of more sparse weights. And from a pragmatic perspective, it's just much faster to compute it. When you have really large models and you're training them on huge data sets for lots of epochs, it really makes a difference if you use ReLUs or 10H, at least computationally. Okay, so let's go and dive into some code to see an implementation of a 2-layer MLP. Okay, so this time what we're going to do is we're going to take a very basic problem, just a regression problem, and we're going to use a 2-layer MLP, which I said it means that there's one hidden layer and one output layer. Okay, so let's formalize a bit here. We have our samples, which are just d-dimensional vectors, and generally our targets are vectors of real numbers in the regression case. So again, we're not trying to predict some kind of class. We're trying to learn a function from d-dimensional vectors, the in-dimensional vectors, to the out-dimensional vectors. Okay, so using the two-layer MLP model, we'll write it like this, like so. So we're gonna first of all define X as a matrix with our samples in its rows. Okay, so we have first of all this weight matrix here, which, like I said, has the neuron weights in its rows. We have a bias term. We're taking the nonlinearity here, which in our case we'll use ReLU. And then we're taking the output of the first this is the hidden layer. We're taking that output and multiplying it by another weight matrix and adding another bias term, and this is our output layer. Okay, so we have a 2-layer MLP. We define H as the hidden dimension, which is the number of neurons in the hidden layer. Okay. It's also the number of activations in the hidden layer, since each neuron creates one activation. Okay, so to make our problem a bit easier, we'll just say that d out is 1. So we're trying to learn a function from some d-dimensional vector to one real number. Okay, and this time we'll use a loss with regularization. So the loss that we're going to use is MSE loss. The reason I chose it is it does work with regression, first of all, and second of all, I'm going to calculate the derivatives here manually, so it's much easier to calculate the derivative of the MSE loss. And we're going to use just a simple stochastic gradient descent to optimize. Okay, so this is our kind of definition of our problem. We have a data set, we have a model, we have a loss function, and we have some kind of optimization algorithm or scheme. Okay, yeah. It's a Frobenius norm. It's just, it's a kind of matrix norm. There are many ways to define a matrix norm. So one way is just to take all the elements of the matrix, think about them like a long vector, and do like a 2 norm of that. Just all the elements squared, sum. Okay. So first of all, we have our model, as we saw, and the main thing that we're going to need, since this is our model, the main thing we're going to need after we have our y hat and we plug our y hat into this loss, we're going to have to calculate the gradient of this loss expression with respect to each of our parameters. So the parameters that we have are W1, W2, B1, and B2. We're going to ignore the biases because we're going to use the bias trick, as we saw before, which is just adding a column of ones. Okay, and further, we're going to ignore regularization now when we derive the actual gradients. Okay. So basically, a thing that you'll see many times is that this kind of notation, it means that basically since what we care about is the gradient of the loss with respect to other stuff, other tensors or intermediate expressions in your calculation, then you just say that if you have this delta of some tensor, it means that it's the gradient of the loss with respect to that tensor. So it just kind of simplifies the notation a bit. Okay. And what you can do is you can really just apply straightforward calculus. That's why I took the MSE here. And you can derive just step by step the gradients for each of the parameters. So basically what we care about, again, I ignored biases here and I ignored regularization. What we care about is this expression, which you can see you just calculate it based on the loss gradient with respect to y hat. Kind of you can see this also makes sense if you remember what the MSE is. It's the difference squared. Okay, so you just take very simple tensor gradients of very simple expressions, and you get this loss, and then you just keep going. The only place you need to kind of take note here is the fact that we have a ReLU function. So the ReLU function again is just one when its input is greater than 0. Okay, so what I recommend you do is just go over, just take this definition, say this is ReLU, and then you'll see that you can basically derive everything by hand really, really easily. Okay, so what we care about is these two expressions, the loss with respect to W2 and the loss with respect to W1. Regarding the regularization, since we have two components of our loss, we have the data loss and the regularization loss, okay, which only depends on the parameters, which is, again, here. So I can derive this with respect to W1, for example, and then I can derive this with respect to W1, for example, and then just add them. Okay, so that's why my final gradient will be just the combination of what I calculated here and the gradient of the regularization term, which in this case is just lambda, which is some regularization factor, usually a small number, times the matrix itself, because it was just the norm of the matrix squared. Okay. All right, so let's look at the code now. The expressions that you saw in the previous slide will be actually implemented in the code. So that's why I showed them. Now let's just define our model. So here we're gonna implement it the most basic, simple way possible, just by creating tensors manually for our weights and doing all the training ourselves. So first of all, what we need is a data set. We're just gonna create some random data. So we have, this is our matrix of samples. We have n samples. Each sample has dn features. Okay, we said dn is 10 just because. These are our labels. So now again, each label is just a real number, and we have n labels, and it's just one number, so the out is 1. These are our matrices for our model, W1 and W2. I added here a dimension for the bias in each one of them because I don't want to manually calculate the bias. It makes everything much longer. This way I can show you I can use the gradient expressions that I showed you in the previous slide and use only them in the code. Okay, so this is just kind of our definition, and now let's really kind of dive into the implementation itself. So this is the whole implementation of the training. Let's see what I'm doing here. Okay, so first of all, remember that I have my matrix of samples X. Okay, the first thing I do is just stack a column of ones on its left side, okay, to get the bias term. Then I matrix multiply it with my weights. Okay, so let's just look at our model. So we have Z, which is X W1. Okay, and then we have the next step here would be apply ReLU. Okay, so I'm using NumPy here, so there's no built-in ReLU, it's just maximum. Okay, so then I have my activations from the hidden layer, which is just ReLU, okay, of Z. That's it. That's the whole forward pass for the hidden layer. Then I have my output layer. So again, I want a bias term, so I'm stacking another column of ones to the output of my hidden layer. And then I'm just computing a matrix product between A. I'm saying that y hat is just A, the hidden layer activations, times my second weight matrix. So that's it. That's all I have to do for the forward pass of this simple two-layer MLP. Okay, so the loss calculation, it's like we said, it's just an MSE, at least the part of the loss that's dependent on the data. So all I have to do is take the difference of these vectors. So this is my target vector, and this is my predicted vector. Just taking their difference squared. Okay, so now I have my loss. After I have that, I have my data loss, which is just y hat minus y, second norm squared. Okay, now that I have a loss, I need to calculate, let's start calculating gradients. So I need, for example, the derivative of the loss with respect to W1 and derivative of the loss with respect to W2. So I showed you the derivation for that in one of the previous slides. So this part basically just implements this directly. Okay, so for example, the derivative of the loss with respect to y hat is just 2 times this difference. Okay, so there's a 1 over n here. Okay, so it's 2 over n this difference of vectors, and so on. So the rest is just according to the derivation that I showed you. Just implemented hard-coded and calculate basically these two tensors. Okay, so D, again, the notation is D something means the gradient of the loss with respect to this something. So this is the gradient of the loss with respect to the W2 tensor. And from that, I can calculate the gradient of the loss with respect to A, and then I can keep going. I have to remove the bias, which is an important note here, because otherwise my sizes won't line up. And I just keep going, and just every time I'm using the previous gradient to calculate the next gradient. This is really a very basic example of the backpropagation algorithm, which you'll see it much more in the lecture, and you'll also implement it in the next homework. Okay, so after I have my gradients, I add the regularization term to the gradient. Remember that I calculated these derivatives without the regularization term. So now I need to add the loss part that's not dependent on the data. Okay, so I take my lambda and my matrix, and then I update my derivative. Okay, and then this is just a simple stochastic gradient descent step, which means take the parameters and move in the negative gradient direction with a step size that's proportional to the learning rate. Okay, that's it. So if I run this, you can see it runs really fast because it's a very, very small problem. So what I have now is updated matrices W1 and W2. So I trained my model, which means I updated my model parameters. If I plot the losses as a function of time, you can see it actually declines. I should have reset the. Sorry, I ran it twice, so you don't see the correct graph. Just a sec. Let's run it again. Okay. So you can see the loss. This is the loss as a function of epoch. So you can see the loss starts really high and really goes down very quickly. Okay, so probably we implemented training correctly. If we would have made some mistakes in our gradient derivation or something like that, then we might not see the loss either go down at all, or it might have even exploded. So this is a good indicator that we implemented it correctly. Okay, so that was a very, very basic implementation. Everything was just in one training loop. So it's not ideal for various cases. Anyone kind of want to point out why it was a bad implementation? Anyone have any ideas? So, okay. So let's start finding the first easy problems that we can find. So it's very, very non-modular. The whole thing is kind of, we said we have components. We said we have a loss function and a model and a data set and an optimization scheme. But basically, the training and the loss were very intermixed because we had to hard code our gradients. So we can't easily change the loss function, for example. If we change the loss function, we have to change our hard-coded gradient derivations. Okay? So same for the optimization. The optimization is part of the training, so it's kind of harder to change. It's hard to extend. For example, if I want to add layers to my MLP, it would be much harder to compute the gradients. That you'd have to see much longer gradient derivations until I reach, for example, from my loss to the first weight parameter. So it would be a very, very long chain of applying the chain rule. And it's easy to get it wrong, basically, if you do it by hand. So I showed it this way because it's, first of all, short. It works. But it's kind of good motivation to understand why you don't want to actually implement anything like that when you implement any kind of more advanced or deep model. So just a quick note, in the next homework, you'll implement an MLP that addresses its concerns, but you'll do it yourself. You have to implement kind of the automatic differentiation and backpropagation and stuff like that in a modular way. So you kind of get how to do it more correctly. And now what we're going to see is kind of see a much higher level implementation that basically uses more features of PyTorch than you saw until now to address these three issues and also create a deeper network. Okay, so let's see how to do an n-layer MLP now. Okay, so again, our usual components here that we mix up is we have a data set, we have a model, we have a loss function that we need to define. Usually it depends on what problem we're trying to solve, and we have some kind of optimization scheme. But like I said, now we're gonna implement it in a more modular way where we can actually intermix these components and change the loss function or change the optimizer without affecting the model, or change the model without affecting the loss or optimizer, and so on. Okay, so first of all, let's load our data set. Again, we'll use MNIST, which is the handwritten digit data set. So now we're going to solve a classification problem. We saw it already before, so this is just some boilerplate code that loads MNIST here. So just remind yourself that in MNIST you have 28 by 28 grayscale images, which means one channel. Okay, so this is our data set now. We're going to solve a classification problem. This time, since we have automatic differentiation and stuff like that, then we can allow ourselves more complex loss functions. For example, cross entropy, which is what we need for this classification task, and we won't have to derive it by ourselves. So that's why I chose a slightly harder problem. Okay, so let's implement our model now. We're gonna see a module in PyTorch called Torch NN. This contains various building blocks for neural networks. It has different kind of layers, for example, linear layers, convolutional layers, recurrent layers, stuff like that you can use just as Lego blocks to build your models. It has lots of different kinds of loss functions that you can just use, again, as blocks to interchange, activation functions, and lots of other stuff. You can explore this model in its documentation. And one of the things it contains is kind of a base class for your own models called nn.module. And when you create a subclass of this class, then you get some things for free. For example, you can register your own tensors as parameters of the model, and you can create models that have kind of various components, as I'm going to show you just a second. And each of these internal components also exposes its parameters so that you can kind of create a composite model and see all the parameters of your model from a top level call of a parameter function. And basically all you have to do is just subclass this class and implement a forward function, and it also gives you a callable object that you can use like it was a function just to apply it on your data and get the output of your model. Okay. So let's look at our MLP class now. So like I said, I am creating a class. I am subclassing NN module. Just look at, from a high level, you can see I only have two methods here. I have an init method and a forward method, okay? So let's look at what I'm trying to do with the init. So what I'm trying to do is create a model that accepts samples of din dimensional dimensions. So we have samples with din features. I want to define a model with multiple layers. So what I'm accepting here is a list of the number of hidden dimensions in each layer. And I want, finally, my model to create D output activations. For example, if I'm solving the MNIST problem as I am here, I would say, for example, I would say din is the number of pixels in my image, and D out would be 10 because I have 10 classes. Okay, so I'm trying to create a probability for 10 classes. So it's again very similar to the multi-class logistic regression that we saw before, but now it's a different model. And the hidden dimensions, like I said, it's the number of neurons in each of the hidden dimensions. So for each element in this list, I want to create a hidden layer with that number of neurons. Okay, so let's look at how I'm building this. Basically, what I'm doing is just creating a list that contains all the dimensions that I need. Just taking my, for example, if I have one hidden dimension of size 100, then I would have, for example, my din, okay, and then I would have 100, which is the hidden dimension, and then I would have my d out. Okay, so what I want to do, I want to create a weight matrix from here to here for this layer, and then a weight matrix from here to here. Okay, is that clear? Okay, so all I have to do is basically use this built-in class. So this is a linear layer or a fully connected layer that we saw before. The way you define it is that you specify how many input dimensions and how many output dimensions, and if you want a bias term. So you can think of this as just a wrapper for the affine transform. Okay, so in this case, this would create a matrix. This would create a matrix of d out by d in, and it would create a bias term. Okay, a bias term which has d out elements. Okay, that's what would happen here. So what I'm doing, I'm just going over my dimensions in pairs. This is what this zip is doing. For each pair of dimensions, I'm creating a linear layer or fully connected layer that just maps, for example, from here to here, and then the next one will map from here to here, and I can put any number of hidden layers here, however number I want. After each linear layer, I'm just using a built-in module called ReLU. Okay, so for every pair, I'm just adding a linear and a ReLU to some list of layers here. And then I'm using another built-in into the NN model called sequential. So this is a container. What you do is just you give it a list of other modules, a sequence of other modules. Okay, and it just creates a module that concatenates them. So the fact that I have a list here of linear ReLU, and then I put it in a sequential means that now I have a module here, this FC property, that basically just applies them sequentially. So it will apply linear ReLU, until there are no more layers to apply. Okay, and then we have another module here, which I define using log softmax. So this is just softmax and then log. So we get log probability. Okay, same softmax that we saw last tutorial. Now we're just combining it with a log. There's a more stable implementation if you combine it. And then you can have, instead of outputting probabilities of your model, you just output log probabilities of your model. Okay, so that's the first part, the init function. It creates all the layers that I need, and it stores them in two properties on my class. Okay, so I have the FC property and the log softmax. And then when I get some data, I get it into my forward function. So what this function will do is just, first of all, it will flatten my data into a matrix of samples. Like I said before, my matrix of samples X should be N, which is the number of samples, by D in, which is the number of features per sample. So I'm just flattening it to that shape. Okay, then I'm taking my samples and applying my fully connected layers. Okay, so this, again, this is the sequential list of linear ReLU. I'm getting my final activation, and then I'm applying the log softmax on that to get predicted log probability. Very similar to the multi-class logistic regression we saw before, only that this is completely different. The way that we get the class scores is completely different now. Okay. So for example, let's create an instance of this model. So here we're just calling our model's constructor. We're giving it the n features. This is the n features from our MNIST data set. So it's just 28 by 28. I think it's 700 and something. This is the list of our hidden dimension sizes, and this is our n classes, which is 10. Okay, let's run that. So you can see if we just print the object that we got, we can see it has these two modules. Module 1, the FC module, is a sequential, which is just, like I said, a list of other modules. Okay, so you have linear ReLU, so on, and for example, here you can see the in features. So this is a matrix that this linear layer will have a matrix from 728 features to 32 features plus a bias term of 32 elements, okay? And then the next linear layer will take those 32 features and then transform it into 64 features, again with a bias term now of 64, okay? Is that clear? So that's what we're doing in this part, and then we're just taking a log softmax of that. So that's why you can see my MLP is composed of 2 modules, and the first module here is composed of some other 10 modules. Okay. So next up, let's print. Since we subclassed the nn.module base class, so now we have kind of a convenient way to get all our parameter tensors. You'll see why this is useful in a second. So first of all, how many parameter tensors do you think we have now? Any ideas? So we have 1, 2, 3, 4, 5 linear layers. Each linear layer has how many parameter tensors? 2. Okay, yeah, exactly. So we have, for each linear layer, we have the weight matrix, which is 1 tensor, and a bias vector, which is another tensor. So we have, per each linear layer, we have 2 parameter tensors. The ReLU doesn't have parameters, so it's a model that doesn't return anything in its parameters. And the log softmax, again, doesn't return anything. So what this will do is just go over all your modules and then return each parameter tensor. Okay, it's a generator that generates the tensors from each of these modules. And then we just count them. We have 10. Okay, and the number of actual individual weights we can see in this expression. If we go over each parameter tensor and count the number of elements in that tensor and sum that, then this is the number of our individual weights. So now I'm actually summing all the neurons in my 5-layer MLP. Okay? So that's how many parameters I have in my model. All right, so let's test the forward pass. Like I said, since we have a forward function and this NN model implements the call magic function, you can just use your model instance like it were a function. When you do this, it calls your forward function. So I'm taking my first image here. X0 is the first image of the MNIST data set, and I'm just calling my module like it were a function on X0. Okay, so now I'm getting a tensor output y hat 0. Remember, this is log probability. Okay, so it makes sense that we have these numbers. Okay, the shape is one sample, 10 features. Why 10 features? We have 10 classes, and we're trying to calculate log probability of each class. Okay, so like I said, if I were to call it like this, forward, it would be the same. If you just call your model like it were a function, it just calls the forward. Okay. Great. So let's move on. Now we have a model. We have a data set. Let's create our loss and optimizer. Now we're gonna basically implement nothing, just use built-ins. So we have in PyTorch various kinds of losses, and there are various ways to calculate cross entropy. I'll just show you something here. Since we have log softmax, what we actually need to do is not really the cross entropy, because we already calculated softmax. So you just need to take these logs and select the correct entry in each vector. Okay, it's like I showed you before in the last tutorial for the multi-class logistic regression. I'll show it in a second. And this time, even though it's a more complex loss function, I'm not going to derive it by hand. I'm just going to use a built-in module called AutoGrad. And it will do everything for me. And we'll also see something that we didn't see up till now, which is the torch.optim module, which implements various optimization schemes, for example, stochastic gradient descent, or other more advanced types of optimizers that you will see later on. Okay, so first, let's create our model. Now, just a more shallow one, okay? So same as before. This is the number of features in my image. This is the number of hidden dimensions that I want, just because. And this is my number of classes. Okay, I'm creating here the NLL, or negative log likelihood loss, okay? Because this loss assumes log probabilities. If you apply this loss to log softmax, it's equivalent to cross entropy. Okay, that's what I said before. It's just this loss. All it does is it takes your log probability vector and returns the entry that corresponds to the correct class. Okay, so minus that actually. So that's why it's really the same as cross entropy, which, if you remember, is minus log of the correct class probability. So that's our loss function. And our optimizer is an object from torch optim, like I said. So we have a built-in SGD. Notice this part here. We're taking our model parameters. So like I said, this is a sequence of all the parameter tensors in our model, and we're passing this sequence to the optimizer. Okay, and these are just hyperparameters. For example, the learning rate and weight decay. Weight decay is a regularization term, like the lambda you saw in my from scratch implementation. So this is the same thing. This is the lambda, and momentum is a kind of a more improved version of stochastic gradient descent, which I think it's in tutorial 5. So we'll talk about that. Anyway, the thing to note here is that the fact that we're giving our optimizer the model parameters. So basically, it doesn't care what our model looks like. It just cares about what parameter tensors belong to it. And you'll see, similar to the example I showed you last time, when you do the backward step, during model training, the gradient of each parameter tensor is calculated automatically and saved inside that tensor. So if this optimizer here has access to these parameters, it will also have access to their gradients. So again, if you remember the optimization step, all you need to do is take your tensor and subtract, for example, the learning rate times the gradient. So if you have the tensor and its gradient, that's all you need. You don't really care about the model. So this is kind of the split between the model and the optimizer. Now let's see how it looks like when we train. Okay. So the only difference now from the loop perspective is that we're gonna go over batches that are lazily loaded because of our data loader. Again, we saw that already. And also note that we only implemented init and forward so far. The rest is just using built-in. So okay, now this is our training loop. So again, it's actually a loop inside a loop, because I'm for each epoch. Let's define it again. The epoch means I'm going over my whole training data set, and to go over my whole data set, I have to go over all its batches, okay? Because my data loader returns batches. I defined some batch size. I don't remember what it was, but I defined some batch size. So when I loop over this object, I get ordered pairs of a sample matrix and its label. Okay, so that's why it's 4 and 4. So first thing I have to do is I take my samples. This is again a batch of samples, and I input it into my model. So this is the forward pass now, because again, remember in the model we only implemented the forward function. All it does is linear ReLU, and then log softmax. So what we have here, ypred, is our log probabilities. Now we have our loss function. So this is the negative log likelihood loss, okay, which I created before. I give it my log probabilities and my target class labels. So this is the number of the class now. And it just, like I said, it selects the correct entry from each of them and sums that. So now I have a loss term, which is equivalent to cross entropy for the multi-class case. Here I'm just summing all the losses so I can print them later. And now the real kind of power of the automatic differentiation comes in. So these two lines here. So first of all, let's look at this. I'm calling zero grad on the optimizer. Can anyone think why this makes sense? Try to think about. Sorry? Yeah, but why am I calling it on the optimizer? Yeah, exactly. So I'm not using my model here. I'm not going over my model and zeroing the gradients for each of the tensors. I'm doing it on the optimizer. Like I showed you before, when we created the optimizer, we gave him the sequence of parameter tensors that we have. So he has a reference to all our tensors. Okay, and what this will actually do is just go over that sequence of tensors, and for each parameter tensor there's a grad. So like if we have a tensor W, which has our parameters, we have a property grad, which is a tensor of the same shape containing its gradient with respect to the loss. Okay? Or with respect to the point where we called backward, more accurately. So first things first, we zero all these gradient tensors if they exist, because like it was mentioned, we don't want to accumulate gradients between batches. Now the next part here is what will actually populate this grad field. Okay? This loss backward call starts from our loss. We calculated some expression, and on the way to this calculation, we used our tensors, our parameter tensors, which all define that they require grad, which is again something that we saw before. So they have some kind of property that says they require grad. So each time you do some operation with them, the operation is recorded, and some of the tensors may be saved for later. Again, it's something that you will implement yourself, so it will be much more clear. When you call loss backward here, it will populate all these grad properties in the tensors, and they will contain the gradient of the tensor with respect to the loss, which is this. So now, in order to update our parameters, we again call an optimizer function, which is step. Again, why does this make sense? Okay, since our optimizer contains a sequence of all our parameter tensors, calling step here would now go over each parameter, take its grad property, okay, and it will do something like this, like parameter minus equals its gradient times the learning rate. Okay, so it's exactly like what I implemented by hand, but this time it does it internally. Okay, let's run this block, see that it actually trains. Okay, so there's nothing really interesting to see, just that the fact that the average loss keeps going down. So just 10 epochs, it's not enough to really get a good result. But since it's a much deeper model, it will take more time to train. But you can see the loss really goes down, so it's a good indication of the fact that it's implemented correctly. And we really are training our model by changing the weights each time toward a lower value of the loss. Okay, any questions about this? Yeah.
If you do too many epochs, this means you're
Depends on a lot of things. Generally, it might be. I mean, for example, here I didn't calculate the loss on any kind of training set. I'm just running for a fixed number of epochs. If you want, you can, for example, calculate after all these batches of the training data, you can calculate your average loss on your test data and see if it starts going up, even though the training loss goes down. For example, it might be a good time to stop training, okay, to prevent overfitting. But here, just a simple example to show the fact that the loss is going down. Okay, any other questions about this implementation? I hope the API is clear, like at least you understand what's going on, because I think it will help you implement your own stuff and do the homework. Okay, thanks.